Today we have Professor Roland Hausser. First of all, let me introduce myself. My name is Alexandre Rademacher. I'm a researcher at IBM and also a professor in Fundação Getúlio Vargas. And here we have Professor Roland in this series of Abraham ao Vivo. The Linguistics Online is an initiative of Brazilian Linguistic Association, and this is designed to give students and researchers. Sorry? The students and research reassess of state of our discussion on most of diverse topics related to the study of human language. So the speaker today is Professor Roland Hausser. He was his last position was as a professor of theoretical and computer linguistics and director of Laboratory of Computer Linguistics in Uni Erling, CLU. He's author of 82 papers, around 82 papers, and 11 books, monographies. Two of them quite popular books, like the Computational Model for Natural Language Communications and Foundation of Computational Linguistics. This topic today is about Database Semantics project, and the aims of the project is to provide a model of natural language communication between agents. So it's a pleasure to have introduced Professor Roland. Professor, it's all of you now. Please take your time, and at the end of the presentation, we have some time for questions. Remember, just to remember people that the questions could be made in the Abrim of is the in the alvivoabrim.org website, and in the YouTube channel, right? And in the end of the talk, we have time for questions. So thank you, Professor. Please, we can start.
Am I on now?
Yes, it's all you now. You can start. Yes.
Can you see my slide?
Yes, we can see your slides.
Okay. The title of my talk is Outline of Database Semantics. And it has 3 chapters. The first one is how language communication works. And my approach is transfer of content based solely on raw data. From the speaker to the hearer, solely on raw data. The second part is technical details of the hear and the speak mode, and includes the data structure of problems, the database schema of database semantics, and data-driven operations based on pattern matching, computational pattern matching. And the third part is critical constructions, grammatical constructions, especially along distance dependency. So the first part is how natural language communication works. To start from common ground, let us begin with predicate calculus as a representation of meaning and content, followed by the DBS alternative. The meaning in predicate calculus is sign-based substitution-driven. In predicate calculus, elementary meanings are treated as mini propositions which denote truth values relative to a set theoretic model. Defined as functors which differ in the number of arguments, for example, fx or fxy, they are connected by propositional operators like propositional calculus and the quantifiers of predicate calculus. For example, the noun dog is interpreted as X is a dog and written as dog X. The adjective little is interpreted as X is little and written as little X. The one-place verb snore is interpreted as X snores and written as snore X. The two-place verb find is interpreted as X finds Y and written as find XY. And the verb give is written as is interpreted as X gives YZ and written as X Y, Z. This allows to represent, for example, the sentence, the dog found a bone, as three mini propositions which are coordinated with the propositional operator and have the variables X and Y bound by two existential quantifiers. So what you how you would represent the dog found a bone in predicate calculus looks like this. There exists an X, there exists a Y, dog X and bone Y and find XY. The different meanings of dog and find are defined by the denotation function F and the assignment function G of a formal model. And the formal model is defined as a quadruple of A, as infinite set of individuals or objects, B, a finite set of basic expressions, F, a denotation function from B into A star, the Kleene star, that's the free monoid over A, and G, an assignment function from variables into A. For illustration, let us define A, B, and F and G as follows. A are the three individuals A1, A2, and A3. B is the set of meaningful expressions, dog, find, and bone. F of dog is this function from the surface into the set of A, or the free monoid over A. So dog refers to the individual A1, find refers to the ordered pair A1 and A2, and bone refers to the individual A2, and the variable assignment of the existential form of the first existential quantifier refers to A1, and of the second to A2. Based on these definitions, the formula is well-formed and true in M. However, if we defined F of dog as A3, as this, for example, the formula would be false. Now the alternative of DBS. In DBS, surfaces from different natural languages may have the same content. For example, for English, German, and French, it would look like this. I'm trying to get... Can I close this window here?
Sure.
So, okay. So this is the content of the dog found a bone. These feature structures are called proplets, and they have ordered attributes, and they are non-recursive. Non-recursive feature structures with ordered attributes are the proplets. They all have an attribute for sir. They have different core attributes for noun, verb, and noun. They have different categories, different SEM values, different continuation values. So, for example, the continuation value of dog is find. Find has the arguments dog and bone has the functor find, like the subject. The subject-predicate distinction is here expressed by the order, and they are all held together by the same proposition number. And this content here is common to the German, der Hund fand einen Knochen, to the English, the dog found a bone, and to the French, le chien a trouvé un os. So in the speak mode, the input to the speak mode is the content as a set of proplets, and the output are the three surfaces. In communication, these surfaces are transmitted to the hearer with the same three surfaces, and they are interpreted as a content which is common to the three surfaces. A content is defined as a set of proplets defined as non-recursive feature structures with ordered attributes connected by semantic relations of structure coded by address. So this find here is the address find 54. This dog here is the address dog 45, 54, bone 54, find 54, and so on. In DBS, the speak mode takes a content as input and produces a surface as output. The hear mode takes a surface as input and produces a content as output. So this is different from predicate calculus in that the speak mode and the hear mode are distinguished. The predicate calculus is sign-oriented, substitution-based, and DBS is agent-based and data-driven. A minimal standard for natural language communication to be successful is that the content mapped by the speaker in speak mode into a surface and the content resulting from the hear mode interpretation of that first surface must be the same. For successful communication in the wider sense, the hearer must infer the speaker's intent by reconstructing the speaker's inference for non-literal content production, resulting in a non-literal meaning to pragmatics. So this is the first principle of pragmatics that's from Foucault. This is Foucault from 1999, and then it had three it had two new editions, came out with Springer. The content is related to both kinds of meaning as follows. The content is a set of connected proplets without language-dependent surfaces. So you see that here. The sur attributes are empty. So this is a non-language content. A content is defined in terms of language. A content is a set of connected proplets without language-dependent surfaces. The connections here are those continuation features. Func is connects dog to find connects to dog and bone connects to find. So this cross copying establishes the semantic relations of structure computationally. A meaning one, a literal meaning, is a content with language-dependent surfaces. The main difference between language and non-language cognition is the presence versus absence of language-dependent surfaces. In language cognition, the transfer of content between agents is indirect by means of surfaces which are attached to content by means of conventions which every speaker and hearer of the language communication had to learn in language acquisition. Non-language cognition, in contrast, is the direct interaction between the agent's cognition and the cognition external environment by matching between concept types and raw data in recognition and action. Language and non-language cognition are compatible and may co-occur, for example, in the command pick the blue square. So when we say to a robot, pick the blue square, the robot has to understand the meaning of the expression, and it has to use non-language cognition to pick the blue square. So language and non-language cognition are very closely related, but they differ in some very important respects. Now, what are the basic notions as compared to propositional calculus, for example? Linguistics, symbolic logic, and philosophy use the following notions. In linguistics, they are noun, adjective, and verb. In logic, the corresponding expressions are argument, modifier, and functor. And in philosophy, the corresponding notions are referent or object, property, and relation. We take it that these notions are not merely different terms for the same things, but different terms for different aspects of the same things. In DBS, the distinctions are related as follows. The semantic referent has the syntactic counterpart noun. The semantic term property has the syntactic kinds adnominal, adverbial, those are the ones which don't distinguish morphologically, and intransitive verb, and relation with the syntactic counterpart transitive verb. The distinction between semantic and syntactic kinds is complemented by a second orthogonal pair of triple distinctions, namely 3 content kinds and 3 associated computational mechanisms. The mechanism of names is a baptism. The mechanism of indexicals is pointing at the agent's online orientation system, and concepts are based on computational matching. The dichotomy is this dichotomy and this dichotomy provide 12 basic notions, 6 pairs. So these are the 12. 3 plus 3 is 6, plus 6 is 9, plus 6 is 12. 6 basic pairs. So this is a pair, 6 of them, and 2 correlations, 1 correlation, second correlation. Theoretically, there are 12 classes of proplets which differ in the semantic, the syntactic, the content, and the mechanism kind. Empirically, however, there are only 6 classes of proplets. They constitute the semantic building blocks of cognition in general and natural language in communication in particular. The 6 classes form the cognitive square of DBS and are considered universal. Here you have the cognitive square. The semantic kinds are referent, property, and relation. The name Fido can only be used as a referent. The indexical this and here can be used as referent or property, and the concept dog can be used as a referent, as a property, and as a relation. Here you have the computational mechanisms associated with the content kinds. So names have the referent have the mechanism of baptism, indexical pointing, concept matching. The semantic kinds referent has the syntactic counterpart of noun, property of adjective, adnominal, adverbial, prepositional noun, and 1-place verb, and the relation 2-place verb and 3-place verb. The most general kind is the concepts here, which occur as all 3 semantic kinds: noun, modifier, property, and relation. The most general semantic kind is reference, which occurs as name, indexical, and concept. The 3 content kinds, concept, indexical, and name, of these, it is the concepts which establish the interaction between the agent's cognition and the cognition external raw data. So if you have a referent, it might be a dog, or a property might be an adjective or a prepositional phrase or a 1-place verb, and a relation is a 1-place or as a 2-place or a 3-place verb. The computational mechanism of concepts is type token matching from philosophy. Goes back to Aristotle. Aristotle's distinction between necessary and accidental properties of something. The indexicals occur in 2 of the 3 semantic kinds. They occur as referent, as in the personal pronouns, and in property, as here or now, but they do not occur as relations. Indexicals depend on the pattern matching mechanism of concepts insofar as concepts are the range of the indexical pointing mechanism. For example, if the indexical points at the feature space veranda of the agent's online orientation system, then the interpretation of the indexical depends on the concept veranda. The mechanism of names is an explicit or implicit act of baptism, which inserts a named reference as the core value into a lexical name proplet. So here you have the proplet of Peter, and then the act of baptism inserts the referent person X in this simplified example. Names depend on the pattern matching mechanism of concepts insofar as the named reference, here person X, consists of a concept and a proposition number. Now I'm going to go and support what I just said with more computational definitions. A content consisting of propoplets with a language-dependent surface value without it is a non-language content. Thus, the content kinds concept, indexical, and name of natural language and their computational mechanisms of matching, pointing, and baptism are the same in language and non-language cognition. Non-language propoplets are used in non-language recognition and action. The following example uses the concept square in agent-based recognition. The type of the concept square is defined here as 4 edges with 4 angles, whereby in the type, these values of the edges, the length is variable, and the angles are all 90 degrees. The type is turned into a token by matching raw data. Raw data, which are defined here, like here, except that the edges have the length 2 centimeters instead of alpha, the variable alpha. So by matching the type onto the raw data, the type is turned into a token, which now has, instead of alpha, 2 centimeters. This is something that really works. In DBS, the explicit definition of concept types, corresponding concept tokens, and raw data relies on the natural sciences, here geometry. Non-language concept recognition may be shown as the following simplified schema. The big box is the agent. Here you have the interface component, not shown. Here you have the raw data. The raw data come in, are matched by the type, and realized as the token. In the corresponding action, the type is adapted to a purpose, for example, drawing a square. The result is a token which is realized as raw data. So action is the result of producing a token, and recognition is the result of recognizing raw data and turning them into a token. The detailed counterpart to 161 is defined as follows. I think this is a mistake. It should be 164. So here you have a type. It is adjusted to a token by the agent's cognition for being a certain purpose. It's passed to the interface component, which turns the token into raw data. What has been shown for the concept square may be extended to the whole class of 2-dimensional geometric objects. For example, a triangle, an equilateral triangle. Here you have only 3 edges and the angle 60 degrees. For the triangle, that's that's the type, because it has a variable here. Here you have the type for rectangle, which we already saw, and here you have the type for square, where the edge lengths should be different. No. Here you have rectangle, and here you have square. In rectangle, you have two lengths, alpha and beta, and in square, they are all the same. In summary, DBS uses automatic agent-based recognition and action for defining content, in contrast to predicate calculus, which uses possible handmade set theoretical models for defining meaning. Now, in the next section, I go through the same routine for the recognition and production of colors. The recognition and production is analogous to those of the geometric shapes. So, for example, blue, the sensory modality is vision. The sensor values are 470 nanometers and 637 terahertz. And then the type is defined as follows, and it is turned into a token by taking the raw data, and because they are in the middle of the interval for wavelengths, they replace the wavelengths in the token by the actual sensor values, and the same for the frequency. Here I say that again in writing, and you have the same correlation between types and tokens. So when the agent's interface component measures raw data, and they match the type of blue, then the type is replaced. Then the intervals in the type are replaced by the constants of the raw data, and the token blue is recognized. The same holds for non-language action. A type is adapted to a purpose and realized as raw data. So if you have a certain type, blue, and it's specialized or adapted into a certain token, and the token is realized as raw data. As a more detailed example, consider the cuttlefish Metisepia pfefferi turning on the color blue using its chromatophores. So here the cuttlefish uses the type blue, specializes it into the token, and realizes in the sensory modality of vision by producing the actuator at 637 terahertz. What has been shown for the color concept blue may be extended to the whole class. So red, green, and blue look alike, except that the wavelengths, values, intervals, and the frequency intervals differ in accordance with physics. In summary, the use of concepts in recognition versus action differs in the origin of the specialization of concept type to concept token. In recognition, the specialization of the type happens in the pattern matching with raw data. In action, the specialization happens in the agent's cognition as an adaptation to the purpose. Now we come to language problems. Language problems, as you may remember, look the same as non-language problems, except that they have surface values. Everything else is the same. So language problems have surface values, non-language problems have no surface problems, but otherwise they're the same. The transfer of content by means of natural language is based entirely on raw data, which are produced by the speaker from a surface token and recognized by the hearer by using a surface type. The following illustrates the transmission of the concept blue used by the speaker in the written sentence, Maria hat ein blaues Auto. So I use a non-English surface to show that this is that this accommodates different languages. So the speaker starts with the type of blue, realizes, takes the surface type, changes, adapts it into a surface token, which is realized as raw data. The hearer uses the surface type to recognize the surface token, which is used to look up the definition of the blue type. So we have the same type token relation in surface transmission as we have in concept recognition between the cognition and the agent's raw data. So language cognition differs from non-language cognition in that it is not the concepts which are produced and recognized from raw data, but the language-dependent surfaces. Language-dependent action is the speakers adapting a surface type into a surface token, which is used for the production of the surface as raw data. Language recognition is the hearer's application of a surface type to match the raw data, resulting in a surface token. The syntactic semantic properties of the content attached to the surface are supplied by the respective onboard memories of the speaker and the hearer. That's here and here. Oops. The syntactic semantic properties of the content attached to the surfaces are not supplied by the respective onboard memories and the hearer. If the speaker or the hearer has not learned these properties of the surface type and the convention connecting them to the appropriate surface, here communication fails. So what I'm trying to say is, in language communication, the speak mode starts out with content types and which are attached to surface types. The surface types are specialized and realized as raw data. The hearer uses the appropriate surface type to match the raw data, turning the type into a token and using the token to look up the content type. This is basically the schema of natural language communication as a transfer of content by means of raw data from the speaker to the hearer. That's all what database semantics is about. Language action in the speak mode, adapting a surface of blah, 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 blah. I have that. Syntactic semantic properties of content attached to the surface are supplied by the respective onboard memories of the speaker and hearer. If they haven't learned that, they can't communicate. The concept blue in a German language proplet may be illustrated as follows. You have a regular proplet. You have the core value, and instead of a placeholder blue in this spot, you use the concept, the explicit concept. So nothing has happened except that the placeholders are substituted by the actual concepts. That's why I had this long speech about concept in the beginning. In the speaker's cognition, the word blaues is defined as a proplet with a German word form surface. The core value is defined explicitly in terms of natural science, optics. The proplet is a concept type, as shown by the use of intervals here intervals of the wavelengths and the frequency values. The speaker's use of the concept type is indirect in that it is not applied to raw data, in contrast to non-language cognition. Language cognition uses concepts indirectly, attached to surfaces. Because the content transfer uses only surfaces, the hearer must supply the recognized surface token with the concept type. So the speaker attaches the concept to the surface, and the hearer attaches the surface to the content. Recognition of a non-language dependent surface type may be shown as follows. Of a language, okay, so the sensory modality is vision, so we are using the print medium as an example. Input raw data, dots on paper. Modality vision is used to look up the surface type. The surface type has the feature placeholder blue, sensory modality vision, semantic field, semantic language purposes, content type, kind, Roman letters, shape type, types blaues. And then we have samples. This surface type is turned into a surface token by taking the raw data input. Surface token, placeholder blue, sensory modality vision, semantic field language surfaces, content kind Roman letters, and now it comes shape tokens, and there you have a token of a B, which has all the accidental properties of a printed letter, you know, the font, the color, the size, and so on. That's why you have these percent signs here, because B is a token. But you can always go from the token to the type by deleting the accidental properties. Consider the realization of the German surface as a letter sequence. The input is a connected proplet with the core value blue, and the same value is passed for positive. Blue, bluer, bluest. The output is the German surface blaues on the computer screen. So here you have the input, and it's recognized as this analyzed surface, and then the output is raw data. That's the production of a surface. So this is in the speaker's cognition. Here it is adapted to the purpose, and here it is realized as raw output. What I'm trying to say is that the recognition and action production of surfaces is exactly analogous to the recognition and production of non-language concepts. Oops. So this was part one. Now I come to the that was sort of the basic setup of the system, all the things you need to realize a talking robot, a talking DBS robot. Now I come to the grammatical aspects. The grammar of database is left associative. The term left associative comes from compiler building in computer science. A left associative composition adds the next item at the end of a sequence and has the bracketing structure you see here. So A is followed by B, AB is followed by C, ABC is followed by D, and so on. DBS uses the following left associative time linear operations in the here mode. Syntax: a sentence start combines with the next word into a new sentence start. So if you have the sentence start, the dog bit, it combines with the next word, the, into the dog bit the. In the here mode morphology, a word from start combines with the next allomorph into a new word form start. So if you have the word form start look, and they have the next allomorph ed, then you get the new word form start looked. In speak mode navigation, a start content combines with the next proplet into a new content. And in speak mode surface realization, a surface combines with the next word surface into a new surface. And we will see that in more detail now. Left associative operations are incremental and strictly time linear. In concord with classical tradition, DBS distinguishes four kinds of semantic relations between properties: subject predicate, object predicate, modifier modified, and conjunct conjunct. So these are the classical semantic relations of structure, and that's all there is, and it's considered universal. There have been arguments that there are no nouns in some languages, but that's in languages that nobody speaks, and it cannot really be verified. The first three constitute the traditional notions of functor argument. These are functor argument, while the last is coordination, conjunct conjunct. The first two are obligatory, subject predicate and object predicate, while modifier modified is optional, and conjunct conjunct is optional as well. DBS shows the classical semantic relations of structure in the here and the speak mode, and in graphical and in linear notation. So the graphical notation is subject predicate is V/N, object V\N, modifier modified is noun down adjective or nominal, verb is down adverbial, and A is down to A. Then conjunct conjunct is expressed graphically as N conjoined with N, V conjoined with V, and A conjoined with V. So we follow the widely adopted view that in coordination, the conjuncts must be of the same kind, and in functor argument, the relation is between different kinds. Right? Here it's between different kinds, and here it's between same kinds. Extra propositional variants are, so these are all intrapropositional, and the extra propositional variants are VV, VV, VN, VV, and so on. Convention. In functor arguments, the lower node in a binary graph precedes in linear notation. So see, here V down N, NV. Here V down N, NV, but different slashes. Here N down A, AN. V down A, AV. So the lower node precedes. And in coordination, the order is as in Western writing tradition. The direction of traversing a relation is indicated by numbered graphs, by numbered arcs in the graph, and by extending the slashes into errors in linear notation. So subject predicate has the traversal arrows 1 and 2. So when you navigate from a verb to the subject, you go down with arrow 1 and up with arrow 2 in this example, and the same in verb object and in noun modifier at nominal and in conjunct. The following examples compare a content in the DBS proplet format, what we talked about before, set of concatenated proplets with the equivalent DBS graph analysis. So take the content of John washed the car. It consists of 4 proplets: John with the functor wash with the arguments person X, John, and car with the functor wash and the modifier new, and new with the modified car. And they all have the same proposition number. Now it gets interesting. Here you see the corresponding graphical representation. So the graphical representation and the proplet representation are strictly equivalent. And you see here the subject-predicate relation characterized by a line and by a slash, and the object-predicate relation by a backslash, and the modifier new by a vertical line. That's the SRG, the semantic relations graph. And it's exactly the same as the proplets. Now, the same can be expressed by using the attributes instead of the values. So this would be the structure, and a more abstract structure than the SRG. It's called the signature, number 2, and has exactly the same slashes. Now we come to the navigation, because in DBS, contents in memory and contents at the now front, we'll come to that, are activated by navigation, by time linear navigation. So the content here is activated by navigating from wash to John, realizing John, from John to wash, realizing John, from wash to car, realizing the car, from car to new, from wash to car, from car to new, realizing car, and realizing the full stop. And these transitions are shown here. John, in the surface realization, these are the numbers of the NAG, numbered arcs graph. These are the surfaces realized, and these are the operations. So John washed the new car, full stop. Didn't do it quite right the first time. The graph analysis uses 4 different views. This is a rehash what I just explained. The semantics relations graph, the signature, the numbers arcs graph, and the surface realization. The following speak mode operations. So the next step is realizing what I just described in principle as computational operations. And this is such a computational operation. The first step, namely the transition from the verb to the subject noun with the down arrow, and it's based on pattern matching. The operation is activated by the by the first proplet provided by automatic word form recognition, John, and matches the second Oh, it's a speak mode operation, sorry. I usually start with the here mode operation because that's more concrete. But anyway, here the first property from the content matches the first pattern, and the pattern realizes John by using the lex-noun rule, lexicalization rule, which produces the surface from a marker that's here in this slot. The operation name here, Vn, is followed by the operation number, that's here. And in Texa, there are 24 examples. Oh. No, cross-referencing doesn't work. That's a nightmare. Okay, can't show it. Normally, I would have gone I don't understand why. Control C. Too bad. Herr Moser? Ja, also Cross-Referencing funktioniert nicht. Wie war der Wundertipp C1? Control 1, okay. Echo. Always good someone. So here you see, we are now in Texa. You see in Texa, there are lots and lots of verb-noun speak mode operations for the subject. And if you click one of those things, then in Texa, you get magically to that operation as it is used in the example 5.4. I can go back there, and then I can go to another instance, navigating from V to N, from love to person Z. So someone loves Mary here, and I can go to where we started from here. We are back in the talk of today. So I just showed you how many subject-predicate constructions there are in the 24 examples of Texa. The next operation is the upward traversal. So the first operation I showed you was this. We are now in the operation number 2. And again, I can go to Texa, which I've loaded before. And you have all the instances of this operation in Texa and the definition of the operation. And so you have, it goes on and on and on. So for example, VV, that's the extra propositional construction with a that clause. That Fido barked, amuses Mary. See, bark and amuse are traversed in this example. So this is just so that you see how database semantics is implemented in the sense of a declarative specification. In computer science, you have declarative specifications which describe the software in a way which can be read by humans, but has a straightforward translation into your favorite programming language. And you have the implementation in that programming language. So declarative specification and procedural implementation. Those are the two aspects of what computer science is about. And computational linguistics in particular, and more particular in database semantics. So here's the number 2 barrier operation. And now we come to the here mode, automatic word form recognition. 3 media, spoken, written, including Braille and signed language. The crucial problem of automatic word form recognition of the input stream into word forms, like here the letter sequence, the old dog looked, into the old dog looked, and then this allows word form recognition. And the word forms in turn require segmentation into allomorphs, like for looked into looked, for such semantic distinctions as number, tense, and mood. In the medium of speech, voice-independent segmentation and allomorph more lookup are the tasks of automatic speech recognition. And in the medium of writing, which is used in DBS, the solution is based on a tri-structure, string search, and a lexicon of allomorphs. And here you have parsing of a complicated word, complicated in the sense that it consists of 1, 2, 3, 4 syllables. And the parsing goes letter by letter in the time linear order. And in the middle, you have things like recognition of but it doesn't last to the end. Then you have undo, as in unduly. And then you finally find the simplex undulate. And so this is the result. Undulate is the surface. The category is nominative, accusative, verb. These are the valency positions. And this is the semantic representative. This is quite old. This is NuCat style. Now, we just had the speak mode. Now we come to the hear mode. The speak mode maps content into surfaces. The hear mode maps surfaces into content. And the hear mode is incremental as well. So it always connects a sentence start with the next word into a new sentence start. So if you have John washed and it gets concatenated in John and it gets semantically interpreted as proplets. So you can run the automatic word form recognition in isolation. Oops, I see our time is almost up. Let me run through very quickly, 5 minutes, okay? So this is a here mode derivation. You have this is the format of it. You have the lexical lookup, word form recognition, and then you go through it step by step, and the operations are of 3 kinds: cross-copying, Here, person X is copied into the arg slot of washed, and washed is copied into the func slot of John, and so on and so forth, until it's strictly time linear and the semantic relations of structures are built in this way. And then finally, the second kind of operation is function word absorption with simultaneous substitution. You see that here. And the third kind is suspension, but that's not part of this talk. But there are three. So here you have the operations which apply here. And then there is a discussion of the onboard memory of DBS. And this differs from conventional database interaction. In conventional database intervention, you have two users, the programmer who puts the content into the database and the user who retrieves the content from the database. But in communication, the speaker produces raw data as a surface, and the speaker interprets it and writes it into the database. So you have two different databases storing the same content by different agent. And there you have the schema of a database. There's three levels of grammatical complexity. So if you have the heavy old car hit the beautiful tree, the car had been speeding, the farmer gave the driver a lift, extra propositional coordination. Then you have clausal connections intrasententially. So the little girl slept, Fido snored. They are connected clausally, but you can all extrasententially, but you can also have them intrasententially. When Fido slept, the little girl, when Fido snored, the little girl slept. And here you have a summary of extra propositional relations between simple sentences. Sentences like John washed the car, Mary read a book, looks like this. And subject predicate that John washed the car surprised Mary. And object predicate, Mary knew that John washed the car, and so on. These are all in Texer, in excruciating detail. And finally, the laboratory setup of DBS, the to-dos, what you have to do, all done in Texer for 24 examples. Here are the examples. And finally, speaker paraphrase, and here ambiguity is something that hasn't been observed so far, namely that ambiguity, several contents for the same surface, is restricted to the here mode, whereas paraphrase, i.e. several surfaces for the same content, is restricted to the speak mode. So you cannot have ambiguity and paraphrase in the same mode. Okay, so here you have examples of paraphrases. John read a book was read by John, and the man gave the child an apple, and the man gave an apple to the child. And then between English and German, Peter read the book, and Peter read the book, and anyway. And finally, you have ambiguity between the nominal and the adverbial reading. You have grammatical disambiguation. And the reason why recursive ambiguity, as in John, who does John say that Bill believes that Mary loves? It has the transitions from say to believe, from belief to love, from love to who, realizing who in transition 9, going back whoop whoop to say, realizing does, John realizing say, believe, say that Bill believes that Mary loves whoop whoop full stop. Anyway, this does not systematically generate recursive ambiguities, because each time the next object sentence starts, the previous interpretation is discarded. Who does John say that Bill loves? Who does John say that Bill believes that Mary loves? Each time the previous object sentence with a non-sentential object is deleted, is cancelled. So in short, recursive ambiguity does not occur in database semantics, which is a relief, because it is necessary for the complexity degree of DBS, which is linear, in comparison to the phrase structure grammars, which are of undecidable complexity. Thank you very much.
Thank you very much, Professor Roland. Let me check. So I have few questions. Actually, I would have many questions, but I will limit myself to just 2 or 3 that are the ones that came to my mind. So the first thing that caught my attention is that you described proplets as something that's not language dependent, right? You have the proplets that's language dependent, but also language independent. But the semantic relations between the proplets are very language oriented.
Well, are you saying they are very special, language special, or are you saying they are very language independent?
No, the semantic relation, the proplets are language independent, but the semantic relation between proplets seems to be language oriented, because we have relations like subject, object,
okay,
or coordination. So these puzzle me. So the structure, the proplets are not language dependent, but the relations between them are very language oriented. Is there any reason for that?
Well, let's go to the example in the beginning here. I forgot how to get the question. Anyway, what is your point about the proplets, please?
My point is about the semantic relations between proplets. You mentioned the semantic relations, the subject, object, those semantic relations.
These relations, yeah, the relations are simply values in certain attributes. So dog is related to find, and find is related to dog. These are cross-references. And
yes, I'm not talking about this cross-reference. I'm talking about the semantic relations between proplets. You said subject, object, coordination, modifier.
Yes.
Right? Those semantic relations are very language oriented, right? So coordination, subject, object, but the proplets are not language dependent. My question is why the semantic relations between proplets are so language oriented, but the proplets are not language specific?
Well, if I understand you correctly, you're saying the proplets cannot be used as an interlingual, let's say. They cannot be used for all languages, and that's true. The example here takes three languages which are closely related, both geographically, historically, and in their structure. So if I take Tagalog, for example, which is an ergative language, the proplets would be quite different, probably, and the relations would be different. But there would still be a possibility of intertranslation, but it would be a lot of work. Here I can just use the proplets for three different languages, and even here there are certain differences between, for example, French uses two words for the imperfect, à trouver, whereas German has fand and English has found, only one proplet. So for French, I would have one lexical proplet more. And then for Latin, for example, a bone, ein Knochen, ein os, would be one word, inflected. So there are these tricky little details, but for semantically similar languages, I can use the same proplet representation as in this example. Did I understand you correctly?
Not exactly. So yeah. So let me try last time. So my question is, remember when you introduced the semantic relations between proplets? You mentioned the relation subject, object.
Yes, the relation. Well, let me go to the proper slides.
Yes, please.
I hope I find it. Okay, here we go. The proplets which I showed you are order-free, and they are stored in the database in accordance with their core value. Now you're asking me, what's the relation between car and find, for example? Well, in this case, it's not find, it's wash. In the database, I have the proplet car with the PRN value 1, and I want to follow the semantic relation of functor argument of subject predicate by going to the wash proplet. The wash proplet is accessed by means of the address. The address is wash1. So I use the core value wash, go down to wash, same proposition number, argument car, and so in this sense, the semantic relation has been used for navigation. it's defined between wash and car, and it's traversed by following the address.
I see. Thank you. One last question for me. You said from the beginning of the talk that the DBS is agent-based, right? So
I followed you up to, I said in the beginning of the talk, and then I lost you acoustically.
So the notion of agent-based is an agent-based notion. So I kind of a puzzle. Yeah, I'm puzzled about what exactly that means. What do you mean by being agent-based?
Okay, I find the right slide. Just a sec. There. Okay, here you have two agents, the speaker and the hearer. Can you see my cursor, my hand?
Yes.
Okay, so the speaker and the hearer, they have bodies, they are out there in the world, they have a cognition, and they have an interface component, and the interface component transports raw data. The speaker produces raw data by means of the interface component in terms of action, and the hearer recognizes raw data in terms of pattern recognition. So in communication, memory or current processing activates the proplet, the concept blue. It is attached to a language-dependent surface. The surface is a type which is specialized into a token. The token is realized as raw data. The raw data are recognized by the hearer's interface component by applying a type to them. It's pattern matching. So I went through that. And then the raw data turn the type into a token, and the token is used to look up the type of blue. That's agent-based.
So agent-based means that the representations are for each agent you own your own representation at a given moment, right? So the representation will be carry on between agents, between agents.
Yeah, yes, I had 36 slides, but I didn't go fast enough. But I thought perhaps explain a little less, but be clear.
Okay, yeah. Okay, so I think that I'll save more questions to the future. Maybe I can write to you offline. I would like to thank you once more for your presentation.
Well, thank you for inviting me.
Thank you very much, Professor Holland, and thank you everyone that's here listening.
Okay. I used to have a bar at the right where questions could appear in print. Are there any questions from the general audience?
No, I didn't get questions from the audience.
Okay. Well, then I think we can.
I think people are shy.
We can stop now, right?
Yes. Thank you very much.
Okay.
Have a good day.
Thank you very much. Now I have to